Good evening, I am Mattia Gianotti from Politecnico di Milano, and today I will present you, on behalf of my colleagues, our work on conceptual modeling of interactive smart spaces. Let's start defining what a smart space and an interactive smart space are. We define a smart space as a physical environment enriched with Internet of Things or other form of digital technology that manage the communication and coordination among different technological components and devices. Then, we define an interactive smart space as a smart space that enables users to interact in multiple ways with the physical environment, its material components, its digital content, its environmental parameters, its sensory stimuli, and its devices, in order to support human tasks. Therefore, an interactive smart space is a smart space where the human plays a much greater role, and thanks to technology, can perform a much wider range of activities and processes at various degrees of complexity. Embracing this human-centric perspective, what characterizes interactive smart spaces with respect to other kinds of smart spaces is the greater amount of interactivity, through multiple forms of human interaction with the physical environment, its material components, and a large amount of multimedia content embedded in the environment. In addition, interactive smart spaces support both automated and human-driven control of multisensory stimuli and environmental phenomena. Whole spectrum of interactive smart spaces can be defined according to different degrees of interactivity, multimedia content, and multisensory stimuli in a continuum that ranges from two extremes. At one extreme, we find digitally enhanced environments that provide limited human interaction with the physical space, its material component, its multimedia content and stimuli, and the environmental parameter, while also offering a good degree of automated environmental control, as it happens, for example, in smart homes. At the other extreme, there are multisensory smart spaces, which offer a high degree of human interaction with the user interacting in a multiple mode, for example by means of gesture, movement, touch, manipulation, or voice, with the physical environment, its material component, its multimedia content, and environmental parameters, providing stimulation for all senses. From a conceptual modeling perspective, many methods have been proposed by academia and industry to support the design of smart spaces, but they tend to focus on technological characteristics. Given the importance of human dimension in interactive smart spaces, these systems call for a novel approach that are more user-centered. A user-centered approach considers the human interaction with devices, multimedia content, technology-enhanced physical objects, and multisensory stimuli as a first-order citizen and enable designers and developers to describe multiple interaction modes and their silent features at a high level in a simple and expressive way, abstracting as much as possible from software and hardware features. Embracing this user-centered view of interactive smart space modeling, our approach regards the conceptual design space for this class of system as organized along two main dimensions. On one hand, we need to model the capabilities of the smart space to support a multiple form of interaction of humans with devices, smart objects, multimedia content, stimuli, and environmental parameters. On the other hand, we need to model the interactive behavior of the user and the technologically enhanced components of the smart space, and how the latter reacts to human action or generates perceivable effects along the time. Consequently, we propose a model composed of two submodels, the structural model and the interactive behavior model. The structural model describes the actors in the interactive smart space that are any agent, human, physical, or technological, that has the capability to execute, react to, or participate in interaction, and specify their capabilities, that is, what they can do, but not how they can do something. The interactive behavior model describes how the actors behave, that is, how they interact among each other, and how these interactions evolve along time to enable the user to execute elementary tasks or more complex activities. The structural model provides conceptual primitives to define two types of actors. Human actors represent different categories of users in the interactive smart space defined by the user profiles, such as child, caregivers, supervisor, and similar. Each actor is also associated to a set of actions they can perform in order to interact with the smart environment and its components. Technological actors represent any digitally enhanced element in the smart environment that enables users' interaction. Technological actors are described by their physical properties and by different capabilities, enabling such interactions: connectivity, identification, sensing, or actuation. Actuation is defined as the capability of generating stimuli perceived by the users, including audiovisual stimuli generated by multimedia content, as well as other sensory stimuli such as olfactory. Technological actors can also use various kinds of digital resources beside digital media, such as software services used for computational purposes. The interactive behavior model describes the behavior of the interactive smart space in response to users' behavior and how such behaviors unfold along time. The interactive behavior model provides various primitives: interaction to describe the effect of user action in terms of UVCA rules that associate user action to stimuli actuated under some condition by technological actors; interaction tasks defined by flow of interactions; activities defined by flow of interaction tasks to describe the orchestration of interaction tasks to achieve a specific goal. Flows are described using standard flow notation in process models such as BPMN. The interactive behavior model also enables to describe behaviors of the smart space resulting from phenomena that are not directly under the user control, by means of SEECA rules related to environmental events to actuation. To exemplify our approach, we quickly present some modeling examples in a case study, the Magic Room. The Magic Room is a multisensory smart space currently installed at 2 schools at 2 therapeutic centers, and designed to engage children with and without cognitive disability in playful learning. This interactive space is equipped with 2 projections, one on the front wall and one on the floor, a bubble machine, a set of fragrance emitters, various smart lights, audio system, a body movement sensor, several smart objects, a set of RFID tagged material, and a huge amount of digital media. Activities are customizable by the caregivers through a web application. This slide shows an excerpt of Magic Room structural model. On the left side, we represent the actor child and its actions on various technological actors. Actions are modeled as progressive level of abstractions. On the right side, we present the technological actor smart sphere, which is a smart object, and its actuation and sensing capabilities. This slide gives an idea of how to model an activity, the Battleship game in this case, using our behavioral model at 2 levels of abstraction. In conclusion, we address a particularly complex type of smart spaces called interactive smart spaces that are characterized by many opportunities for the user to interact with space, its component, and a vast amount of multimedia content and stimuli. We propose a conceptual model that embraces a human-centric approach and acknowledges the importance of integrating the representation of both human and technological actors and relating users' action with sensing and actuation capabilities of the various elements of smart space. The model defined so far is only an initial step, and several modeling refinements and extensions are needed, which are the focus of our current work. The updated version will be evaluated empirically and already planned an empirical study involving 50 young designers and ICT engineers to test the usability, completeness, and expressiveness of the model. Thank you for your attention.